Hello, my name is Swetha Kotha, and I'm a data scientist here at TIBCO Software. This is a demonstration of the Risk Management Accelerator, a ready-made template to predict and assess risk in any business or analytics context. TIBCO's Risk Management Accelerator allows anyone, from a non-expert to a data scientist, build an end-to-end system that analyzes and detects anomalies from live streams of data using machine learning models. We're going to show how easy it is to build and even deploy these models using TIBCO's visualization and analytics platform, Spotfire, as well as TIBCO's real-time data ingestion platform, Streaming.
The models and following investigations are configured from the Spotfire template. We'll walk through an existing risk dataset on credit card transactions. This dataset contains transaction information for various customers. So credit card companies must be able to quickly detect and address unauthorized transactions in order to retain satisfied customers. We're hoping that some of these data fields can help predict whether or not a transaction is fraudulent. The last column here, target, indicates whether or not each transaction is fraud, labeled with a 1, or not fraud, labeled with a 0. To start, we simply just want to know how many fraudulent cases are in our data. So it appears that 6% of the data, or 37,000 cases, are reported to be fraud, and that around 59,000 cases are not fraud. Now, let's further explore our data. In general, it's good practice to understand how our data is distributed, how our data fields associate with the target variable, and also how they associate amongst themselves. So from both the map as well as this categorical distribution chart, I can tell that the majority of transactions in our dataset are in the United States. And on the bottom here, I can view a numeric variable like normalized age account against our target. So this tells us that fraudulent transactions are mainly distributed in younger accounts compared to non-fraudulent transactions. And on the next two pages, we can view how our categorical variables are correlated with each other and how our numeric variables are correlated with our target. Here, it appears that account 24 hours is the most positively correlated variable with our target. This is the number of times a customer's account was accessed in the last 24 hours. So what we're seeing here is that as that number increases, so does the occurrence of fraudulent transactions. Altogether, these types of explorations help discern which variables to include in our models. Now that we've explored our data, we'll take a look at our models. The supervised model is a random forest that finds patterns in nonlinear data and can handle unbalanced and high-dimensional data. So here, we selected to use all our variables as input to the model. And we want to predict whether target equals 1 or whether a transaction is fraudulent. I'll click Run. We can view the top predictors from the model and the corresponding breakdown of how that predictor's distribution contributes to the probability of being a target in the partial dependence plot. So interpreting partial dependence plots varies case to case as they show the average prediction when only a single feature is changed and assume no correlation between features. So here, we observe that as the scaled number of transactions in the last 24 hours increases, the risk also steadily increases. In addition to understanding how this model predicts, we can also assess our model results. So we hope that the blue curve in the ROC plot falls close to the green line, and that our predictions lie near the actual probabilities in these two plots. Now on the previous page, we have a confusion matrix based on a heuristic cutoff from 20% of the data that we test on. Here, we're predicting if the target is 0 or 1. So the random forest will output a probability between 0 to 1, and by default, anything above a 0.5 cutoff is categorized as fraudulent, and anything below a 0.5 threshold is categorized as not fraudulent. So we could use this 0.5 threshold, but in practice, that may not always be beneficial. So what if we end up turning away customers by investigating too many low-risk events? Or on the other end, what if we find out that we're actually neglecting too many high-risk events? Well then, how do we use our model? So in practice, our trained model should be used to best predict future outcomes.
But most importantly, we realized that we might want to be more or less cautious of categorizing a case as fraud or not. So let's reevaluate this deterministic zero point 0.5 threshold. Now, we give you a few different options here to choose thresholds for whether or not a new case is fraud. Here, you could choose a threshold for maximum F1. A F1 score closer to 1 means we have a more accurate model that has low false positives and low false negatives. In the optimal threshold chart, a user can define their own metric on the y-axis that varies with the predicted probability. And lastly, in the cost function chart, you can define your own costs for a false positive, incorrectly labeling a case as fraud, and for a false negative, missing a fraud. So say that we decide that the cost of incorrectly labeling a transaction as fraud is low. It costs $1. But the cost of missing a fraud is high. It costs $5 or 5 times as more. That is, we might irritate a customer through further investigating a proper transaction, but we're more cautious because we know from experience missing fraudulent transactions can be a costly ordeal. So we adjust these numbers as we see fit. And then we can either take the minimum cost cutoff shown here or choose from the chart anywhere where our cost function starts to elbow upwards. Here, I've selected our minimum cost cutoff, and I can also see how all other metrics, including the confusion matrix and the F1 scores, conveniently update. I'll select this cutoff for deployment.
What if we don't know in advance which transactions in our training data are fraudulent? We need a model that does not rely on our target data field. Here, we have an unsupervised model based on principal component analysis, or PCA. PCA is a dimension reduction technique that reduces the number of variables in our data while still retaining as much information in the newly transformed data as possible. These new data fields are called principal components or factors. We again have full flexibility to choose which variables to include in our PCA model.
Upon running our model, we can explore our transformed data. Most of the information within the original features is compressed into the first components after running PCA. So that's why we explore how our data and features fall along the first two principal components here. And we also explore how the data falls along the first principal components pairwise within the factor space. Here, each point is a transaction from the data set after normalization. Cases that fall far away from clusters are potential indications of fraud. This is because our PCA analysis has compressed regular data into similar spaces, but irregular data might fall elsewhere.
We define oddity as the distance between a point and the data center. In the case where our PCA analysis points appear in a single cluster, we measure each point's distance to the origin, since again, we've normalized our data. In the case where PCA points fall in multiple clusters, we measure each point's distance to the nearest cluster. In order to calculate oddity, we need to know two things: how many clusters there are, and also how many components or factors should we use. To determine how many clusters there are, we simply look at these images of our factor space. So it appears that most of the points fall in a single cluster. To determine the number of factors, we simply look at the factor plot. We want to find the elbow in this plot. So here it looks like the elbow is around 10 factors. This indicates a plateau in the information retained from the original data. So now I'll update these parameters and I'll hit calculate oddity. The oddity metric is being calculated for each point in the background. In the model results, we can again define our own use case specific oddity threshold. Using Spotfire's markings, I'll drill down into the oddity distances. So it appears that the distances seem to subdue around 35 or so. I'll set this as our oddity threshold. This threshold we defined can now be used to separate anomalous transactions from regular ones.
We've defined exactly how we want our models to operate on new data. Now, how do we actually put these models to use? So far, we've worked to train our models on historical data, and we define use case specific thresholds. In conjunction, these can be used to label new real-time data without any further expert intervention. We can deploy both of our models to TIBCO streaming using the send supervised model and send unsupervised model buttons. These models are deployed to an AMS server. We approve both of these models, and then we simply deploy them. Now, we'll start a simulation that mimics new transaction data flowing through our system. So we can view this incoming data in TIBCO Live View or in our own dashboard. On the left, we have our supervised model, and on the right, we have our unsupervised model. What we're seeing here is our models scoring new cases as they come by, and we can clearly see which ones are crossing the thresholds that we previously set. Going back to our dashboard, you can further explore which cases were flagged by our model, and you can list the cases by risk level and decide for yourself whether to assign them for further investigation or not.
But risk management is not just for finance or banking. You can use this accelerator for any risk management scenario. Now, we'll use it for healthcare. We've easily swapped out the previous dataset for a completely different one. This is heart disease risk data.
Now, I'll jump to the random forest model. It's configured using Spotfire's inbuilt R and Python data functions. I simply change the parameters we want to input to the model and then run it. Heart disease risk data handles high stakes variables on patient safety. So I'll set the cost of missing such risk to 100. Our cutoff is now much lower than what it was before. And we see from the resulting confusion matrix that no patients in our test data who were actually at risk of heart disease were missed.
The beauty of TIBCO's Risk Management Accelerator is that it's versatile across verticals and use cases. The accelerator allows non-experts from any industry to detect risk events in real time using TIBCO Spotfire and TIBCO Streaming. But we don't just give you the bare bones of a model or deployment system. We provide all the tools you need to customize an end-to-end data science solution, from data exploration to model configuration to case investigations for your specific business problems. If you're interested in learning more or using the accelerator, take a look at the accelerator page that accompanies this presentation.